the currents and the voltages for the case where the machine represented by non-classical model and the machine represented by classical model, this relation can be applied also. Now for small signal stability study, we can linearize the equation, and to have the change in I and V, these two equations can be used. Now the total system equation that describes the behavior of the system, which in our case it is the 3-machine 9-bus system and variable with voltage T and mechanical torque and T is time. Now for the software development that we are used to decide about the stability of the system can be summarized as follows. We have run the static load flow program to get the system data that we need to compute the matrix A prior to the disturbance. Once we have obtained it, here we have some equation that we have computed, then we have inputted the matrix A using the software package MATLAB, and we have found the eigenvalues to be as follows, where we have considered 4 cases. The first case, we have taken that machine 1 as being represented by classical model and the rest by non-classical model. Then the system was found to be stable because of the real part of the parts that describe the bare-board system are to decide about its stability was found to be all negative. And this is valid for damping constant as being equal to 1 per unit, or for damping constant to be equal to 0. And the second case treats the machine where we have considered the second machine represented by classical model and machine 1 and 3 presented by non-classical model. In here, we have found that our system can say that it is not stable because there is some poles which are located on the right hand of S-plane, and this gives you the instability. This we can say that this modeled in our project. As conclusion will be presented by my colleague.
As conclusion, in the present project, we have in the present project a complete theory using as a conclusion a complete theory. As a conclusion, a complete theory has been developed to study the 9-bus system impedance diagram. As conclusion, in the present project we have studied
As conclusion, we can say that the system or the objective that we have concerned to get is reached. Now what we propose as further study is to take a well-modeled excitation system to force the system to become stable under any disturbance. Thank you for your attention, and your questions are welcome.
Thanks for your clear presentation, and now we go to questions. Mr. Hassan, do you have any questions?
You stated in the introduction that the mechanical power was assumed to be constant during the transient period. What facts or what's the reason behind this assumption?
when the power is assumed constant, because when disturbance happens, we can assume it, we can neglect.
Always as being constant, because, and this is due to the time constant that takes the whole system within the turbine and even the boiler, and so it takes time. And the transient state doesn't take a long time. It is valid only for a few seconds at most. For this reason, and in the classical, as it is clear that in classical we decide about stability only during the first swing.
You mean by that the time constant for the feedback loop to operate
yes.
is
Longer than
the time
yes.
transient?
Yes.
also, on page 85 and 86, you study machine 1 classically represented, 2 others non-classical,
Yes.
then machine 2 classically, 2 others non-classical, then machine 3 classical,
And so on.
and so on. When you start, machine 1 represented classically, 2 others non-classically, you obtain perfect eigenvalues with
Yes.
just have time. Stability
It's okay.
is okay. Now, for the same disturbances,
Yes.
when you take machine 2 classically represented, the 2 others non-classically represented, as I see here in the result in page 85 and 86, I think that's 85, whether the damping is equal to 1 or damping equals 0, I see that all eigenvalues have negative
Yes.
real part, which means stability, except the second one, which is called lambda of 8, lambda of 8 in both cases.
Which
You can
case?
look page
Which case?
85, second case,
Okay.
page 85 and 86.
Yes. Yes.
You found that the imaginary part was 0. Okay? You can look back at your results if you want, it's all right.
Yes.
The real part is 0.0001, which means about 10 to the minus 1.
Okay.
This is lambda of 8, okay?
Yes.
Now, in the preceding case where machine 1 was represented classically, lambda of 8 still had an imaginary part, almost 0, as you can see,
Yes.
and the real part also almost 0.
Yes.
You are saying then in the second case when machine 2 is represented classically, you have instability or at least show errors of accuracy of computations.
Yes.
In both cases, with damping equals 0 or with damping equal 1, so with or without damping, well, if it is the only place when I would hesitate before saying that I have instability.
Yes.
But while in the third case now, the same story happens. In the third case, when machine 3 is represented classically,
Yes.
still lambda of 8. You see, with no damping, you have real part and imaginary part 0.
Yes.
So I would even conclude differently, say lambda of 8. So even if the second machine is represented classically, I still have stability.
Yes.
Even though you have the real part 0.0001, because you see, well, even if the machine 3 is represented classically, still precision of computations cannot allow you to conclude that instability. Now, thirdly, when machine 3 is represented classically, it's the one represented classically, you conclude instability. Fine, but it's not because of the lambda of 8. It's because you have 2 or 3 or 4 other eigenvalues
Sure.
which have real parts.
Yes. Yes.
So represented by non-classical
Yes.
or clues. What are the results? You get stability or instability for small
We
signals.
have obtained one eigenvalues or one pole situated on the right plane.
Which one? Is it still as before lambda?
Yes, lambda 4. You can check.
Okay, it's not lambda of 8.
Lambda 4. For the case where all three machines are presented by non-classical model.
With or without damping? With no damping.
With and without damping, we have obtained only one result positive. The lambda 2. Lambda 2.
And with the
Yes.
with damping,
This system, we can say that it can be marginally stable.
because one only has small real part. What general conclusion do you draw from something? This is a classical network which has been studied in textbooks
Yes.
and in many ways, but it was studied by just generator 1 represented classically and the 2 others non-classical.
Yes.
Out of your study,
More details of the excitation system, because whenever you have instability or something which is marginally, you are obliged. Yes.
involved.
Yes, marginally stable. You are obliged to do some controllers and even some